Now that we've seen how Newton's law of universal gravity works, we need to face a puzzle that it raises. The gravitational force gets weaker with distance, but it doesn't disappear completely. And with two fairly big bodies like the Earth and Moon, the force is quite large even if they're 400,000 kilometers apart. So if the Earth and Moon are pulling on each other with this large force, you should be asking yourself, why don't they simply crash into each other? What's holding the Moon up? Newton worked on the same problem, and he came up with a very nice way of understanding what's going on. So we're going to follow his argument here. Start by thinking about what happens when you fire a cannonball straight ahead. Not up or down, just level with the ground. If we ignore details like the resistance of air, then the cannonball does two things. It keeps moving forward at a constant velocity, and it falls towards the ground with a constant 9.8 meters per second squared acceleration. So long as it doesn't start out tipped upward or downward, it doesn't matter how fast it's fired, it will always fall at the same rate. That means that as long as the ground is level, the cannonball will always hit the ground in the same amount of time. Let's say that this is 1 second. So whether it's fired fast or slow, in 1 second it hits the ground. If it's fired slowly, then it hits the ground close to where it was fired from. If it's fired with more force, then it hits the ground further away, but still just 1 second later. However, that's only true if the Earth remains flat. We know that if we look on a big enough scale, the Earth is round. So if we fire the cannonball with enough force, then something funny will start to happen to it. Instead of taking 1 second to hit the ground, it will take longer, simply because the ground has curved away from it. The faster the cannonball leaves the barrel, the farther it travels. And the farther it travels, the longer it takes before it hits the ground, because the ground has curved farther away from it. Finally, if the cannonball leaves the barrel at 8 kilometers per second, it falls at the same rate that the Earth's surface curves away from it. Curve C on the diagram shows this. The cannonball never gets any farther from the Earth's surface than it started out, and it keeps going around the planet, falling under gravity, but never quite hitting the ground. This is what we call an orbit. So when a spacecraft or the Moon orbits the Earth, it hasn't escaped the Earth's gravity. Instead, it's falling just as much as an object near the ground falls when you let go of it. However, it's that high velocity parallel to the ground that keeps it from hitting. So the Moon is falling around the Earth, but it keeps missing the ground. Lastly, if the cannonball leaves the barrel at a little more than 8 kilometers per second, it pulls away from the Earth, slowing down slightly as it gets farther away. Eventually, it slows down enough that the Earth's gravity starts pulling it back towards the ground, causing it to speed up again. However, it always has enough forward motion that it doesn't hit the ground. It completes an orbit by coming right back to where it started with the same speed it started with. This oval-shaped path the cannonball follows is an ellipse. We'll look at ellipses more closely in a couple of slides. I should mention here that I'm using that number 8 kilometers per second, and that applies to anything in low Earth orbit. In other words, orbiting just beyond the bulk of the Earth's atmosphere, a few hundred kilometers above the ground. However, a spacecraft in a higher orbit, or the Moon, would have a slower orbit speed because it's farther from the Earth, so it isn't falling under gravity as quickly. Also, if you're orbiting another planet, moon, or star, you'd have a different orbit speed because the body you're orbiting would have a different gravitational pull as well. In summary, an orbit requires two things: the gravity of the Earth, or whatever else is being orbited, and the speed of the orbiting body. This is what allows the orbiter to fall around the body it's orbiting instead of simply crashing into it. This works for the Moon or a spacecraft orbiting the Earth. It also works for the Earth and other planets orbiting the Sun, and even for the Sun orbiting around the center of the Milky Way galaxy. So if a spacecraft in orbit is still feeling the Earth's gravity, why do the people in and around it just float around? The reason is that they're in freefall. In other words, they're falling, but everything else around them is falling at the same rate. This is just like a skydiver on Earth jumping out of a plane. Until they open their parachute, they're in freefall as well, and people can see them float around. In fact, a person in a spacecraft in low Earth orbit is falling as fast or faster than the skydiver, since the spacecraft doesn't feel air resistance slowing it down. The one difference is that the spacecraft is also moving at several kilometers per second parallel to the ground, so the Earth curves away before it hits the ground. This picture shows folks floating, but they're not in a spacecraft. Instead, they're in a NASA aircraft known as the Vomit Comet. This plane flies up at an angle, and then they shut off the engines and let the plane coast in a big freefall arc. For 30 seconds at a time, the people in the plane can float around inside until the engines come back on so they don't hit the ground. When Newton worked out how orbits behaved using his laws of motion and gravity, he knew he had it right because of the work done earlier in the 1600s by Johannes Kepler. Kepler had developed a set of laws that described how planets orbit around the Sun. Kepler didn't have Newton's laws of motion, but he did have the best data available on how planets moved in our sky. Kepler found that he could only make sense of where the planets were in the sky if their orbits followed a specific pattern around the Sun, and his 3 laws of planetary motion describe that pattern. The first law says that planets orbit the Sun in a shape called an ellipse. Notice that this is the same shape we described earlier for a cannonball orbiting the Earth. There are a couple of important numbers that we should mention that describe ellipses. We use these numbers to describe orbits. The first number is called the semi-major axis. This is the average distance between the orbiting body and the thing being orbited. Do you remember what we call the average distance between the Earth and the Sun? Click forward when you've got your answer. Did you get it? The average distance between the Earth and Sun, that is, the semi-major axis of the Earth's orbit, is called an astronomical unit. The second number that describes elliptical orbits is the eccentricity. Eccentricity is a measure of how far from a circle the orbit is, and it ranges from 0 to 1. If the orbit is a perfect circle, that's an eccentricity equal to 0. As the orbit gets more elongated, the eccentricity gets bigger. As the eccentricity approaches 1, the orbit gets very long and thin. Finally, an eccentricity equal to 1 means that the orbiting body can completely escape out into space. We'll look at escape a little later on. Kepler's second law of planetary motion says that as a planet gets closer to the Sun in its orbit, it goes faster than when it's farther away. Once again, this matches up with what we saw with Newton's cannonball discussion. Here's a diagram showing Kepler's first 2 laws. The overall shape is an ellipse. The Sun is offset from the center, so that the planet is closest on the right side and farthest away on the left side. This ellipse is more eccentric than most planetary orbits. They're mostly very close to being circles. Also, the planet moves faster when it's closest to the Sun. The 2 shaded wedges represent the motion of the planet over the same period of time. Notice how much farther the planet moves on the right side than it does on the left. Kepler had one more law of planetary motion, and this one talked about how one planet's orbit relates to another. He found that there was a relationship between the size of planet orbits, the semi-major axis, and the time it takes the planets to go around the Sun, the period. The period squared is proportional to the semi-major axis cubed. Newton was able to match Kepler's third law with his own description of orbits, and he was able to extend it as well. Newton argued that the reason Kepler's third law worked was that all of the planets orbit the same body, the Sun, and it's the Sun's gravity that dominates the time it takes them to orbit. Since gravity depends on mass, we can use the motion of the planets to figure out the mass of the Sun. This is a very powerful idea. I'm not going to have you calculate this, except as an extra credit option, but it's important to understand the idea because it's the key behind how we measure the mass of most things in astronomy. So if you want to know the mass of an object, just look at something orbiting it. To find the mass of the Sun, just look at the orbit of a planet. To find the mass of a galaxy, look at the motion of a star orbiting that galaxy. Of course, not everything has something orbiting it. For example, Mercury and Venus don't have moons. We can still measure their masses by seeing how their gravity affects the motion of other things like the Earth, but this is much more challenging than simply looking at an orbiting body. This also illustrates the difference between Kepler's and Newton's laws. Kepler's laws describe the motion of planets, but they didn't give much insight into what caused planets to move that way. Newton derived the same motion from a much more general description of how all bodies moved. In doing so, he was able to show that similar rules applied to all orbits, and that you could use this to get a deeper understanding of objects in space. Pretty amazing, eh? Here's another question that lets you work on the connection between an object's mass and the orbits of things going around it. You'll need to think about how a planet's orbit works and how changing the mass of its star affects how fast the planet has to move to stay in orbit.